Hello class, in this video we're going to talk about how to craft a linear program problem into a mathematical presentation, and then we're going to learn how to solve that linear program problem through the graph, and then that will tell us the simplex algorithm in solving the linear programming, which is already built in the Excel solver. So after we're doing that, we're going to move to Excel and to see how to solve the problem within Excel solver. So let me first give you a very brief description of the problem. Suppose you are making furnitures, these toy furnitures, table and chairs. For each table, you need some basic resource as input to assemble them together. So you need small blocks and large blocks. Here is the requirement of resource. So for example, for a table, you need 2 small blocks and 2 large blocks, as you see here. And for chairs, you need 2 small blocks and 1 large block. And the total amount of small and large blocks are given as this. And you also need a label to assemble the material together. This is the label requirement, and this is the total amount of label you have. For each unit of table you sell, you can earn $57, and you also have to pay for the cost for raw material. So then you get these 31 as your net profit of selling one table. Similarly, you can get a net profit of selling one chair. Then the problem is how many tables and how many chairs you produce to maximize the profit. So as you see here, there are 3 pieces of information here. First is decision variable. What's the decision you are trying to make? In this case, it's the number of tables and chairs to make. The second is objective function. What are the matrix you are going to measure the success of your decision? In this case, is to maximize the net profit. And also we have constraints. What holds you back that you could not make any amount of tables or chairs as you want? The reason is we have label constraint. That means we only have this amount of workers available, and we also have constraint on our small and large blocks, which are the raw material we have. Now we're going to write these objective function and constraints into a mathematical representation. So to ease our definition, we define the symbols. T represent number of tables, C represent number of chairs. For each table, we earn $31. For each chair, we can make $19 as your net profit. And this is the resources requirement as well as the total amount of resource we have. So given that, we can write down our objective function, which is to maximize our profit. The profit has 2 parts. First is the profit from selling tables, and then the second part is the profit of selling the chairs. The next one is the label constraint. As we see here on the left hand side, this is the total amount of label you use. 3T, which corresponds to the label used to produce T number of tables, and 2C, which corresponded to the label used for producing C unit of chairs, and this has to be less than the total amount of label we have. Similarly, we can write down the constraint for small blocks. These are the total amount of small blocks you use, because for each unit of table you have to use 2 units of small blocks, and for each chair you produce you need 2 units of small blocks, and the total amount of small block you use has to be less than the total amount of small block you have. Similarly, we can write the constraint for large blocks, and we have this physical constraint, meaning the number of table and chairs you made has to be non-active. In this case, we assume T and C to be continuous variable, which is mainly for the purpose of trackability. In the next class, we are going to talk about the constraint of being integer that make the problem difficult to solve. But now let's focus on continuous variables. So So from as you see here, from this side to this side, we formulate from a problem described by words and tables into a mathematical permutation, and this will help us to solve the problem once we write this in a mathematical format. That's a very critical part of modeling, actually. So given this is our problem, how are we going to solve this? The idea is to plot decision variable into a graph. So on the x-axis, we have number of chairs, and in the y-axis, we have number of tables. So for each point on this graph, which would represent a possible solution. For example, in this case, it represents 5 chairs and 2 tables. That means you can produce 5 chairs and 2 tables. In this case, it represents one chair and 2 tables. So as you see here, every point on this graph represents a possible decision. Then the question is, how are we going to represent those constraints on this graph so that we know which points is feasible? The idea is to draw this line on a graph by setting this equal to be equal. In this case, the line we draw is this. Since it's a linear function, so it will be a line. There's a trick to draw this line, basically because a line is determined by 2 points. So as only as you find 2 points on this line, then you can determine this line. The most easy way is just by setting the line, by setting the point where they would own these axis or y-axis. For example, if you set c equal to 0, that means y-axis, then the t is, if c is 0, then t is 11 over 3. That's this. This is the first point you get. And the other point you can get is by setting t equal to 0, then c equal to 11 over 2, which is 5.5. This is the second point, and if you collect these two together, now represent the label constraint. And there's another question is which are the points? What are the points that satisfy this label constraint? So actually, because this is it's less equal to terms, and these coefficient positive, meaning if t and c reduce, then this term on the left hand side would reduce. So because this line represent the point that make this less equal to be exactly equal, then these points that is below this line will be the point that satisfy this unequal constraint. For example, in this point, it represents 1, 10, 2 table. So it use 3 multiplied by 2 plus 2 multiplied by 1, 8 hours of label together, which is less than 11. So this point would satisfy this label constraint. So that means all these points that is below this line would satisfy this constraint. Similarly, if we look at this point, it has 5 chairs and 2 tables. So the total amount of label hours used is calculated by this, which is 60 hours. Now violate the constraint. So these points that is above this line will not satisfy the constraint. Similarly, we can draw the constraint on small blocks. It looks like this, and the point that satisfies these two constraints together is the intersection of these two regions. And next, we're going to look at the label constraint, the large block constraint, and the constraint will looks like this, and the intersection between these two regions is given by this. Lastly, we are going to look at the physical constraint, and it removes this negative region. So this is our feasible region because every point in this area would satisfy all the constraints we have. This is called For example, in this point, there's 2 chairs on 1 table, and the first constraint calculate the number of label used is 3 multiplied by t, which is 1, plus 2 multiplied by 2, which is 7. So the label used is less than total label hours. Similarly, we can calculate for small blocks. The small block used is 6, so it satisfies the constraint. For large block is 4, so it's less than 6. So given this point, we can evaluate profit of this objective function. So it's 69. So for every point, we can do the same thing, and then to find the optimal solution, basically is to, if you are going to use a very brute force way, is to evaluate every point in its feasible region and compare the profit to find the largest one. That's basically the idea of finding the optimal solution. But that's a very stupid way. Simplex will be a much simpler way. You will see later. Similarly, if we evaluate the point that is out of the feasible region, we will find that some of the constraint would not satisfy. So if you see here, this point would not satisfy the large block constraint because it's above the large block constraint line here. This is the constraint for large blocks. As you see here, is beyond this line. So even though we can still evaluate the profit, but since this point is not feasible, so we can never earn this amount of profit actually. We call this region a feasible region. To find the optimal solution, we need to think about how to fit the objective function onto the graph. The key is that we don't know what the exact profit will be, so we can't draw a line to represent this. But what if we suppose that the objective function equal to, say, any number 62, then we can draw a line, and we can call this as an iso profit line, because every point on this line would have same profit of 62. And we can also figure out the slope of this line, which is just done by moving this term 90 multiplied by c to the right hand side and divided by 31. Then we get a slope of this line. In this case is this. And as you see here, the slope is not decided by these numbers 62 by this 62 per se, because for every iso profit function it will have the same slope. So then we get the idea of how to draw this profit function on a graph. It's basically a graph, basically a line with a slope of this negative 0.61 with unknown intercept. Right? Since we are going to maximize the profit, so we want to move up this profit function on the far right, on the upright direction as far as possible, because these coefficients are positive, we want to make as many tables and chairs as possible. So if you see here, this is a solution. We have 4 chairs and 0 tables, and compared to the previous one, we are moving up these objective function up. We get a profit of 76. We can further move this line up, and the solution will be at this point, and these 0 chairs and 3 tables, so we find that profit will actually increase. As you see, we can continue to move up this line, as you see here. Okay, we can continue to move up this line. Now this line seems to touch the feasible region, meaning we have no we couldn't move this line up again because otherwise we will get out of the feasible region. The solution we get will no longer be feasible. So this point actually will be our optimal solution, which corresponds to two tables and two chairs. The profit we earn is 100. And this is our optimal solution. If you do a close observation here, the optimal solution is only going to be at the corner point, because if it's in the middle, there's always chance that you can move the objective up or down. If so, there is a very famous um, theorem in linear programming that is the optimal solution is always at the corner. In this case, we have these four corners, and instead of evaluating every point in its feasible region, which will be very computationally difficult, we'll only need to evaluate these corner points. In this case, we only have four polar points that will reduce the amount of computation significantly, and the computer we can write a computer algorithm to figure out what are the corner points, and this algorithm is called simplex, which is proposed by this professor George Dantzig. And now the INFORMS, which is the most prestigious conference among the professors from industry engineering and business school, and there is a Dantzig Practice Award to the faculty members who have made a significant contribution in both the theory of simplex and application of simplex method in real problem, and is listed as one of the most important 10 algorithms for the century. And it's not. And now, if you look back of this graph, the simplex algorithm is actually not very difficult to understand. Right? It basically says the optimal solution is always going to be at the corner point. So for the next part, we're going to talk about the sensitivity analysis. The idea is, what if, for this model, what if some of the parameters change? For example, what if the price for chairs change? How does the solution change? What does the total amount of label increase? What does that have change our solution? So these are called some sensitivity analysis, which is very, I would say, as important to as equally important as getting the optimal solution, because most of the time these sensitivity analysis are the place we get our insight from the model. For example, the first sensitivity analysis is to increase the resource amount we have in terms of labor hours. For example, you hire additional workers, part-time workers. What's the value of that additional labor? So as you see, the labor constraint originally is 11. If you increase to 12, then the labor constraint would move upwards, because now you have more resources. You have a large region of feasible. You have a large feasible region. So in the case, labor constraint will shift up. But as you see here, since the labor constraint is not binding, meaning you don't actually use up all the labor you have, then hiring additional labor actually would not influence your solution. So in this case, optimal solution and profit would remain the same, because the labor constraint is not binding. Let's look at another sensitivity analysis. Change the number of small blocks from 8 to 10. Similarly, okay, let me see. So this is the original constraint for small block. If you increase the amount, as you see here, the small blocks constraint shift up, because now you have more small blocks. As you see here, this original optimal solution is no longer a corner point, and the objective function now have the opportunity to shift upwards again. which in this case is at this point. So this is going to be our new optimal solution, which corresponded to 4 chairs and 1 table. And our profit is 107. If you remember, our original profit, optimal profit is 100, so it increased by 7. So that means 2 units of additional small blocks would increase our profit by 7. But this is not always true. If you get the number of small chairs to say 20, then the optimal solution would not increase proportionally, because if the small blocks amount continue to increase, then it would no longer be a binding constraint if the amount of small block is so huge. So for the next one, we're going to change coefficient for the chairs. For example, the chairs, let's say share price increased by 31. Now this coefficient of chairs become 50. Then the changes we have for this problem is the slope of our objective function now become minus 50 over 31, which is much more steeper than the original solution. So then if you move the objective function, you actually end up with this is the point where the objective function touch the feasible region. So this will be our new optimal solution. We have 0 tables and 4 chairs. That makes sense to you, right? Because now the price of chair increased significantly, so you would produce more chairs than tables. So here's the summary of the sensitivity analysis. We change the number on the right-hand side, which corresponds to the amount of resource we have. Now we will see this will lead to the change of our solution. But changing the resource of a non-binding constraint would not lead to the change of optimal solution. We'll also change the number in our objective function, which will change the slope of our objective function, which might lead to a new optimal solution. So that's all for this toy problem, and we illustrate a simplex algorithm with a graph and do some basic sensitivity analysis with the graph. So now we're going to move to Excel to see how Excel going to solve this problem ultimately, and how Excel will do this sensitivity analysis for you.